Okay, so this is the 19th lecture. So in the previous lecture, we were talking about the weak law of large numbers. So the weak law of large numbers asserts that the probability of adherence to the mean converges to 1. So this can be interpreted as asserting that as we wait longer and longer, deviation from the mean becomes more unlikely. So you can see I have the mathematical formulation of the weak law of large numbers written out here. In the middle of the screen, we have random variables x1, x2, x3, which are independent and identically distributed. That's the fundamental hypothesis which underlies the laws of large numbers, independence and identical distribution for this sequence of random variables we're observing. When thinking about the law of large numbers, it's usually natural to think that the indexes on the random variables represent timestamps from the experiment, or they represent your first observation and your second observation and your third observation and so on like that. It's your usually the indexes are associated with repeatedly observing the same quantity, and the index on the random variable is the place in your list at which you observed it. And so we have these independent and identically distributed random variables, and then we have some positive error tolerance epsilon. And so epsilon is this standard notation in mathematical analysis for an error tolerance. And what we're seeing here is that the limit as n goes to infinity of the probability that the sample average minus the mean has an absolute value less than or equal to epsilon is equal to 1. So that's the weak law of large numbers. It says that you have an IID sequence of random variables and some positive error tolerance. And then with probability approaching certainty, the sample average will be within that error tolerance of the mean. So in this lecture, we're going to discuss the strong law of large numbers, which asserts that adherence to the mean is eventually certain. So this can be interpreted as saying that deviation forever is impossible. So we can have a look at the strong law of large numbers, which says that if we have an IID sequence of random variables, the probability that the sample average converges to the mean is equal to 1. So we have this certain event which says that the sample average converges to the mean. And so the basic idea of the strong law of large numbers is that it tells you that with probability 1, the sample average you observe will eventually stabilize at the mean. So the probability that you have a fluctuation forever or you have convergence to some value other than the mean, or you have infinite growth, all of those things have zero probability. The only possible outcome is that the sample average converges to the mean. And so the strong law of large numbers doesn't tell you exactly how fast the sample average is going to converge to the mean. Um, and there are a lot of other ways you can get information about that, notably the central limit theorem, which we'll discuss next week. But it does tell you that there is some point at which the sample average is going to be really, really close to the mean and never leave it again. So this gives you a really extensive amount of information about the possible behaviors of probabilistic averages, because you have this sequence which is necessarily convergent. It can't have any of the numerous other properties a sequence of real numbers can have. If you have a sequence which is the sample averages of a probabilistic experiment, then it has to be a convergent sequence of numbers, and moreover, you know exactly what it's converging to. You know, it's converging to the mean of the random variable. Okay, so the strong law of large numbers implies the weak law of large numbers, but it's significantly harder to prove, and we won't address the proof of the strong law of large numbers. It's what you would call a pointwise ergodic theorem, um, as opposed to a mean ergodic theorem. But these kinds of concepts are way beyond what typically gets taught in an elementary probability course. And the proof of the strong law of large numbers, as opposed to more general concepts of an ergodic theorem, is something that could be done in one lecture. I was planning to do a lecture on that before various circumstances happened that delayed the course a little bit, but it the proof of the strong law of large numbers really is quite technical, and um, I don't think it necessarily gives a lot of insight into why the strong law of large numbers is true unless you study it in a much more general context. So, we won't address the proof of the strong law of large numbers, but I will point out that the proof of the weak law of large numbers was very straightforward using Chebyshev's inequality, and that method just doesn't address the main issue needed to prove the strong law of large numbers. Okay, so the strong law of large numbers has many important conceptual consequences, but probably the most important one is the idea that if the sample average is stabilizing around some value, then it is likely to stay there forever. So, what this looks like in actual science is the principle that the average of a sample is a reasonable proxy for the average of the population. So it's like you have your sample with what you see as the empirical average of the sample, and you assume that the empirical average you observed for the sample is the underlying average for the population. And the reason that's mathematically plausible is because the strong law of large numbers tells you that once the average has stabilized at the mean, collecting more and more observations is only going to result in stronger and stronger confirmation of what the mean is, and stronger numerical concentration of the sample average from the mean. So it's like if you take 1,000 observations and you get some average, and then after 2,000 observations, the average is about the same, and after 3,000 observations, the average is about the same. You can, at that point, think that what you're seeing is the strong law of large numbers, and the average that your sample history has stabilized at is the underlying mean of the random variable. And so the average is going to stay there forever. And collecting more observations about this random variable would just result in more concentration towards the average. So you can certainly look at other parameters like the variance or the correlation with other things, but if you're just interested in the average of the sample, the strong law of large numbers tells you that usually there's a pretty hard limit on how much data you actually need to collect to figure out what the average would be with an arbitrarily large data set or a data set that exhausts the entire population. So, if you want to get some sort of statistics about the population of the United States, it's what you usually see is the results of some sort of random sample average. And the hypothesis is that because of the strong law of large numbers, the concentration of the sample average represents the average of the entire population, because both of those empirical averages, the local empirical average from the sample and the global empirical average for the entire population, both of those empirical averages should be very close to the expectation of the underlying random variable. And so taking the local average with the sample gives you pretty much all the information you need to know about the global population. And in a similar context, if you were doing some sort of chemistry experiment and you wanted to figure out the properties of a certain reaction, what you would do is you would perform it over and over again and try to isolate specific parameters. And then you would take the average of your various experimental trials where you did the reaction many times and you observed the same thing, and then you would take the average of all the trials and assume that the strong law of large numbers holds, and the average of your trials would represent the average of an arbitrarily large number of trials. Okay, so we can have a look at this example. So we're going to make the basic assumption that we're always making with the law of large numbers, where we say that x1, x2, x3 are independent, identically distributed random variables with the expectation of x1 equal to mu. And because these are identically distributed, they all have the same expectation mu. So when we're discussing sequences of independent and identically distributed random variables, it's pretty standard to write mu for the common expectation of all of these random variables. And so, what we're saying about this particular sequence we're considering in the example is that it has a positive expectation. And we want to show that it's impossible for the sample average to keep taking negative values arbitrarily far in the future. So, one way of thinking about some of the consequences of the strong law of large numbers is that it forces a dichotomy where events that have to do with the long term sample average are either impossible or certain. So, if you have a condition on the sample average which is consistent with the mean, then that event is certain. And if you have a condition on the sample average which forces it to be different from the mean, then that event is impossible. So here we have this situation where the mean is positive, and we're asking about the probability that the sample average keeps taking negative values arbitrarily far in the future. So this situation falls on the wrong side of the dichotomy, and so it's impossible. So let's try and write or think of a more detailed mathematical explanation for why this is impossible. So we want to think that there's arbitrarily large values of n such that the sample average is negative. And we want to show that this is inconsistent with the hypothesis of the mean being positive. So we think that no matter how far we are into the future, there's always some further future where the sample average comes out to be negative. And what we can deduce from the strong law of large numbers is that there's some time t in the future so that at any time past t, the sample average has to be at least half of the mean. And the reason for that is because the limit as n goes to infinity of the sample average is equal to the mean. And so if you think about the concept of a limit, it says that eventually the sample average falls within any interval of positive length around the mean. So it's like you have the mean and the mean minus a half, and or the mean and the mean minus the mean over 2. So you're picking some points less than the mean. And the definition of a limit says that if I pick any point less than the mean, I know that the sample average eventually has to exceed that, and it has to keep exceeding that forever once it's reached that point. So, what we're doing here is we're kind of writing out a probabilistic interpretation of the definition of a limit, which is that there's some time such that after that time t, the sample average is above the mean over 2, because we know that this would happen no matter which quantity less than mu we pick. So mu over 2 is just a convenient example of a positive quantity less than mu. I could also pick mu over 3, or I could pick mu over 4, or I could pick 3 mu over 4. I could choose any positive quantity less than mu. And the definition of a limit would tell me that there exists this time t, so that if n is greater than t, then the sample average is greater than or equal to mu over 2. And we can see that if n is one of these arbitrarily large values exerted to be negative, then that's inconsistent with what we've deduced from the strong law of large numbers. So the thing that we're showing is impossible is for the sample average to keep taking negative values arbitrarily far in the future. And the reason we know that's impossible is because the strong law of large numbers tells us it's certain that the sample average is eventually positive. And since these things are inconsistent, we know that it's impossible for the sample average to keep taking negative values arbitrarily far in the future. Okay, so we can look at another example of how the strong law of large numbers produces this really tight connection between long term sample averages and the expectations of random variables. So, what we want to think is that we have two sequences of random variables x1, x2, x3, and y1, y2, y3. So we have these two IID sequences, and we're given that the common expectation of the x sequence is 4. So usually with IID sequences, when people stipulate the expectation, they just write the expectation of x1, or if they started counting from 0, they might write the expectation of x0, and it's understood that by indicating this initial expectation, you've stipulated the common expectation of the entire sequence of IID random variables, because the hypothesis of identical distribution tells you that the expectation of the first one is the same as the expectation of the second and the third and all of them. Okay, so we're given that the expectation of x1 is 4. And so we're supposing that the ratio x1 added up to xn divided by y1 added up to yn stabilizes at -6. And we want to determine the expectation of y1. So, what we can think here is that the expectation is at the most intuitive level the real value of the random variable. It's like you have a random number, and if you had to pick one deterministic specific value and say my random number is just a perturbation of this, you pick the expectation. And so what we can think here is that if we pretended there was no randomness actually involved, and we just substituted the expectation for the random variable, we would get n times the common expectation of the x's divided by n times the common expectation of the y's. And so the n's would cancel out, and this ratio would tell us the ratio of the two expectations. And we can see the strong law of large numbers justifies that line of reasoning. It tells you that the long-term sample average of the y's stabilizes at the expectation of y1, and the long-term sample average of the x's stabilizes at the expectation of x1, which we know is 4. And therefore, we can look at this ratio of sums as a ratio of averages because the two ends cancel out. So, what we would do is we would have x1 through xn divided by n divided by y1 through yn divided by n. And the two n's would cancel out, and we see that the ratio of sums stabilizes at the ratio of expectations. So the ratio of sums stabilizes at 4 over the expectation of y, and we can see that minus 6 equals 4 over the expectation of y1. And so we can see the expectation of y1 is minus 2/3, which will also be the common expectation of all the y's. Okay, so let's say now we have this sequence of IID random variables, and we want to determine the long-term average value of x2k minus x2k plus 1. So we can see that what we're asked about here is we have this random number which is being observed over and over again, and we're asked about the average value of the difference between the sample and or the even sample and the odd sample. So what we can expect is that because this is the same random quantity being observed over and over again, any difference in one direction between the even and odd should be canceled out by a subsequent difference in the opposite direction between even and odd, because the even and odd observations are the same random phenomena. We've just chosen to separate it out into two different time segments. And so, for that reason, we can think that heuristically, this long term average difference between even and odd should be 0. And we can try to justify that with the strong law of large numbers. So we can see that the odd sequence and the even sequence are each individually identically distributed independent sequences with the same expectation, because we produced this splitting into even and odd from a single sequence of IID random variables. And therefore, we can look at the quantity inquired about in the question, which is the long-term average of the difference between even and odd. And so when we're looking at the long term average of the difference between even and odd, we can split it up into two different sums, the long term even average and the long term odd average. And then we can apply the strong law of large numbers to each of those averages individually, and we see that it comes out to be mu minus mu, which is 0. So again, this kind of illustrates the principle of the strong law of large numbers saying that the mean is like the real value of the random variable. And if I just plugged in the mean for x2k and x2k plus 1, I would get mu minus mu, which would be 0. And so the strong law of large numbers provides a mathematical justification for the most fundamental heuristic in probability, which is that the expectation is the value that best represents the random variable. And the way that gets observed is through long-term sample averages converging to the mean. Okay. So let's have a look at this example where we're thinking about the restrictions that independence and identical distribution place on sample averages. So we have this sequence x1, x2, x3, which we're just understanding as any sequence of random variables. And we're supposing that the long term sample average takes values greater than 1 and less than minus 1 arbitrarily far in the future. So we want to explain why this sequence of random variables cannot be IID. So it's telling us that if you have a long-term sample average which is consistently fluctuating, then the hypothesis of independence and identical distribution has to be invalid. So either there are correlations between your random variables which are causing the sample average to fluctuate, or you have the failure of identical distribution where some of the random variables have expectations that are maybe growing to infinity, or at least variance going to infinity, or something that's telling you these are not just the same finite parameters observed over and over again. So, what this example can be thought of is kind of a message that long term fluctuation in the sample average is inconsistent with independence and identical distribution. Okay, so we can suppose we have this sequence of IID random variables, or well, where the expectation is mu. And we want to understand why it's impossible for the sample average to fluctuate to values greater than 1 and less than -1 arbitrarily far in the future. So we can think that the strong law of large numbers tells us that since the sample average is greater than 1 at times arbitrarily far in the future, the mean has to be greater than or equal to 1. But we can apply exactly the same reasoning to say that since there's arbitrarily large n where the sample average is less than or equal to -1, the mean has to be less than or equal to -1. So these assumptions are inconsistent. You can't have the mean being less than or equal to -1 and greater than or equal to 1. So we see that you can't have an IID sequence where the long-term sample average consistently fluctuates between large positive values and large negative values. The only way you could have a long-term sample average taking on both positive and negative values arbitrarily far in the future is if the mean were 0 and those values were getting smaller and smaller, such that the sample average was converging to 0 with small positive and negative fluctuations on either side. But there's just no way a long-term sample average can keep going greater than 1 and less than -1 for a sequence of IID random variables.